Okay, so hello everyone. My name is Hector Posada. I'm a PhD student of the Politécnica University of Catalunya from the Department of Civil and Environmental Engineering, and today I'm presenting MatchFEM, a computational design assistant tool for digital twins of building and infrastructure. First of all, I want to introduce you to the digital twin vision that we have adopted in our research group. This is a BIM-based virtual representation of physical systems that integrates multiple layers of information. It reflects their environment and processes and continuously leverage real-world data. Considering this vision, it is expected that the digital twins help us to interact and implement all the data layers that are associated to a specific asset during its whole life cycle. These are 3D BIM, which is the foundational data layer, planning and scheduling, structural analysis, and so on. So considering this vision, we can identify four problems regarding digital twin data generation. The first is, how many software do we need to interact with all these information layers? How much it costs to have all this proprietary software? Do we have the professional expertise required? And how long it takes to generate such an information construct? So, based on these problems, we established the objective of this study as the simplification and optimization of the generation of digital twin data within a unified environment while maintaining data integrity, promoting open standards, and reducing the required level of specialized skills. Our proposal to achieve these objectives is the MatchFEM tool, which is a computational design Grasshopper plugin designed to simplify the data generation of digital twins. MatchFEM is built in Grasshopper to leverage its powerful geometric engine and its intuitive visual programming Canva. In its current version, MatchFEM helps us to interact and implement 3D BIM, planning and scheduling, structural analysis, data processing, and IoT monitoring. All the scripts related to creating IFC or editing IFC were developed using the C# open source library, the EC3 toolkit. This is a general overview of the MatchFEM plugin. It contains a set of components that help us to interact with the previously mentioned data layers. And for instance, in this script, we built an entire IFC of a bridge with just a few components of MatchFEM. Now let's navigate through each of the data layers that MatchFEM incorporates. First, the 3D BIM. With MatchFEM, we can generate different types of IFC geometry following the IFC 4.3 standard. For instance, we can generate swept solid, swept dissolid, facet BREP, advanced BREPs. It is worth to point out that not so many BIM software allows the generation and the read, or the proper read of IMC advanced BREPs, representation that is key when we deal with complex geometry and we don't want to compromise the IFC size file. So if we generate IFC geometry, we have to add metadata to it. With MatchFEM, we can initialize IFC bridges on IFC buildings, and we count on a set of components to also incorporate material, site, geometry, IFC beams, and so on. Regarding planning and scheduling, MatchFEM implements the control and process domains of the IFC schema. It's possible to create a comprehensive work schedule with multiple tasks linked to specific IFC elements. For IoT monitoring, it's possible to incorporate IFC sensor at specific locations with the corresponding linked element and interact with IoT platforms. Currently, we have included APIs of two IoT solutions. One is the Mainflux open source IoT framework, and the other one is Arduino Cloud, which is widely used in academia. Users can get the things that are available in the IoT platforms, get the IoT data as well, create new things, and upload data as well. So if we have IoT data, we have to process this data to gain insights. That's why we conceive a data processing module, which is a set of tailor-made processing scripts for specific applications. In this case, we have the processing of strain gauges data and LVDTs to process deflections and match measured values against predictions. This can be relevant in real-world scenarios such as slab post-tensioning and bridge load testing. And last but not least, we have the structural analysis data layer. It's possible to generate structural analysis models following the IFC schema. We can leverage the geometric capabilities of Grasshopper to mesh surfaces and generate finite shell elements. This is a resulting structural analysis model for a steel profile. And these IFC models can be imported in any commercial software that allows the import of this data into the system, for instance, SAP 2000. Okay, so now that we have explained in general the characteristics, functionalities, or MatchFEM, let's get into a comprehensive case study of MatchFEM implementation. Let's imagine that we have a contracted firm that aims to monitor the construction of a concrete footbridge structure, with a focus on tracking project progression and concrete compressive strength using the maturity method. This method allows us to predict the compressive strength at early ages, measuring on-site temperatures data. The footbridge features two spans with doubly curved slab deck elements, and the structural designer provided 2D drawings during the design stage. Let's help them through a digital twin. So, with the 2D drawings and the capabilities of Grasshopper, we can generate the geometry, and with MatchFEM, we can create an IFC semantically rich 4D BIM. Regarding geometry and metadata, the slabs of the deck were generated using IFC Advanced BREP, and each of the elements have a volume associated. For the metadata, each of the IFC elements are classified within the predefined types of the IFC schema. For planning and scheduling, we had a detailed schedule in an Excel file. We imported this data into Grasshopper and generate a work schedule and multiple IFC tasks linked to the corresponding IFC elements. For IoT and data processing, as the objective is to monitor the temperature to estimate the compressive strength at early ages, we located 4 temperature sensors in each of the slab decks, and at the same time we created 8 variables in Arduino Cloud to facilitate the retrieval of data and the BIM IoT integration. So once we set the IoT monitoring, we can process this data with the maturity component of MatchFEM that process the maturity curve of the concrete that will be used in the construction, and it can process also the on-site temperatures to predict the compressive strength. And if we want to gain more insights, not only the updated mechanical properties of the concrete, we can generate a structural analysis model and import it into SAP 2000 to perform a deflection analysis with the current mechanical properties of the concrete. MatchFEM have been validated not only in hypothetical scenarios, but in our research group. It also helps us to develop real-world cases of digital twins. These are the construction of an office building in Barcelona, the railway bridge load testing in Extremadura, Spain, the maintenance of a composite road bridge, the scan to BIM of a heritage railway bridge in Catalunya, digital twin of a Gaussian ball roof, and digital twin of a doubly curved Catalan roof. In conclusion, MatchFEM streamlines digital twin data generations. In a unified environment, we can interact with multiple layers of information. It's expandable. We can add more features, more capabilities, and more data layers. In academia, the tool supports student training in IFC, in IoT monitoring, and also allow us to develop laboratory digital twin practices. And for research, the plugin can generate large IFC data sets. This can be relevant in topics such as AI fine-tuning or bin-to-fan automation. The plugin have full documentation in a Gitbook online and is free for download. We encourage you to download the plugin, test it, we need feedback, and also we are open to book demos. Thank you.